Continuing with section 7.1, this is the third video or third part of the video. So we did part A of example 4, and now we are going to look at example 4 part B. So now the function is 6t plus e to the minus 3t plus 5t cubed minus 9. Now t, we have not evaluated the Laplace transform of t. If we were to, we would have to evaluate this integral over here. So integral going from 0 to infinity, t times e to the minus s t dt, which is not that hard to evaluate, so it shouldn't take you long to do that. But at this moment, I want to show you that we can also use tables or already, calculated transforms table. So we will look at that and finally be able to figure out what the transform of our given function is. So for t, here I have a brief table. Why I say brief? Because these are just few functions whose transforms are given here, and also their domains or the condition on S for which these are applicable or these exist. There are other functions whose transforms are given at the end of the book, and if you ever need to look at them, you may go to the end of the book. It's the end on inside of the back page of the book. So you see here we have the one function is 1, transform is 1 over s. This is something we calculated. Function is e to the at, transform is 1 over s minus a. S is greater than a. So these are the transforms we already calculated or computed. Now what about t to any power? So the transform will be n factorial over s to the n plus 1, where n is the power on t. So this is something we could use for the first term here. So the t, we have 6t, so power is 1, so that we get 6 times t, n, which is 1, n factorial or 1 factorial, which is 1, divided by s raised to the power n plus 1. So we get s squared. Plus, so the next one will be 1 over, remember, e to the at transform is 1 over s minus a. So here it will be s minus negative 3, which makes it s plus 3. Now note here that if we have s 1 over s minus a, then the domain will be s is greater than a. But if I have s 1 over s plus a, then we have s is greater than 0. We do not say s is greater than negative a, because s cannot be negative. Okay, so going further, now the third term here is 5t cubed. So again, we have to use the formula for t to the n. So with n being 3, so the transform will be 3 factorial divided by s raised to 3 plus 1, which is 4. Then the last one, negative 9, which is similar to what we did in the previous example with 11. So we end up getting 9 over s. So we simplify 6 over s square, because the constant was 6. So 6 times 1 is 6, plus 1 over s plus 3 plus 30. How am I getting 30? Well, 3 factorial, remember, is 3 into 2 into 1, which is 6. So 6 times 5 is 30 over s to the 4, and then minus 9 over s, where s is greater than 0. So now, by looking at each domain of each transform, we have that the maximum we can say is that s is greater than 0 for the whole expression, for the whole transform. Now we will evaluate a couple of more examples looking at these formulas or using this table. So it says find the Laplace transform of the given function. The first one is 6e to the minus 5t plus t square e to the t plus t e to the 3t cosine of square root of 5t. So if you look at the first one, this is something we have been doing quite a few times. We have seen this kind of function. So the Laplace transform will be 6 over s minus negative 5, which makes it s plus 5. And for the next one, t square e to the t. So can you see can use this one here, which is saying n factorial over s minus a to the n plus 1. So it is very similar to the just t to the n. The only difference is now where I have s, it will be converted into s minus a. So what is a here? A is 1. So I get 2 factorial, which is the power on t, which is then, and divided by s minus 1 whole to the third. Plus the next one, cosine square root of 5t, and then e to the 3t. So remember again, same thing, s minus a. So a is 3, so s minus 3 divided by s minus 3 whole square plus 5. Okay, now the next one. So this should be simple. So we have only no product, just single function in each, and you can see. Now the limits again, remember for the first one, we have for the first expression, we have s is greater than 0. For this one, it will be s is greater than 1. For the last one will be s is greater than 3. So the domain here will be s is greater than 3. So this is true for s is greater than 3. The second one is true for s is greater than 0, and you should be able to see why. Okay, so now some other information, that the Laplace transform also exists for piecewise continuous function. So what are piecewise continuous function? I don't know if you guys have heard it before. I mean, like I know you might have heard about piecewise function, but what is a piecewise continuous function? So we say one thing is they are defined on closed intervals. So we say that a function f of t is said to be a piecewise continuous function on a finite interval a, b, with a and b included, if f of t is continuous at every point of a, b, except possibly for a finite number of points at which f of t has jump discontinuities. So we do allow jump discontinuities, but we do allow discontinuities, but they can only be the jump discontinuities. Another important thing is that the function must be defined at every point of the interval, and of course at the end points as well. Now a function f, in other words, we can say a function f of t is said to be piecewise continuous on 0 to infinity if f of t is piecewise continuous on all intervals 0 to n for all n greater than 0. So n can be, you can pick any value and it should be continuous on that interval. So here is a picture of a piecewise continuous function. So in kind of other terms or other words, you can say a piecewise function is a function which is continuous everywhere, but except where it has some discontinuities, which are the jump discontinuities only. So let's see. The question is saying determine whether f of t is continuous, piecewise continuous, or neither on the interval 0 to 10, and then sketch the graph of f of t. Looking at the first one. Now, in order to check continuity, remember we check the limits. So the first thing is that in the first example here, a, well, remember we want the function to be continuous on this interval. So it must, first thing is that it should have a value at 0 and 10. And this function does not have a value at 0 and 10. So it is not continuous. It is not continuous because it doesn't have values at 0, 5, and 10. So is it piecewise continuous? Let's see. So in order for it to piecewise continuous, again, the first important thing is that it should have values at the endpoints, which is 0 and 10, and we don't have that. So this is neither continuous nor piecewise continuous, so we will say neither. Okay, and when we graph the function, well, the problem is that this is starting at a very high value, which is out of our bounds, but we will try to see how we can represent this. And we might have to like kind of say we blow out one area and then we're looking at the other portion in a separate axis. So let's say this is 5 and this is 10 and this is 2. So then the first part, that between 0 and 5, it has a value 2. So there is a hole here and there is a hole here. And now from 5 to 10, it has the value 0. So it means we come here, it has a hole here, all these points, and then a hole here. Okay? And then the other part is the e to the 40, which will be somewhere high up here. And it will have a hole because the value does not exist, and then the exponential growth. So this is now you can see there are jump discontinuities at 10, at 5, but why is it not, definitely it's not continuous, but why is it not piecewise continuous? The reason is because we don't have the values. It is not defined for all values on 0 to 10. So it is neither. Okay, looking at the next one. So how do we look at this? Well, the first thing is that we can simplify it by factoring. So on the top I get t minus 2 times t minus 1. At the bottom I get t minus 2 times t plus 2, which gives me, well, t minus 2 cancel, so I get t minus 1 over t plus 2. Okay, so what about this one now? So we could have, so since we cancel the t minus 2, so we will write here t is not equal to 2. So we do not have a value at 2, and we do not have a value at negative 2. Well, negative 2 is not inside our interval 0 to 10, so we don't worry about that. But 2 is in our interval, right? 2 does exist in our interval 0 to 10, but it does not have a value there. So we can say that it is also neither. So if we graph it, this is how it will look. It will have a vertical asymptote at negative 2. So let's say this is negative 1, this is negative 2, this is 1, 2, 2, 3. Okay. So we have a vertical asymptote at negative 2. We have a horizontal asymptote at 1. Okay. What about the x-intercept? Well, x-intercept is at t is equal to 1. Y-intercept will be negative 1/2. Or you should have said t-intercept here. So negative 1/2, so somewhere here. So this looks like the function is going to go like this here. And then a part of the function will be up here. So we are not concerned about the portion which is to the left of the y-axis, because remember we are looking in the interval 0 to 10. So we are starting from here and going up to 10. So if you can see what is missing here, something is missing. Remember we said t does not have a value at 2, so what do? We erase it a little bit and then put a hole there. So at 2 there is a hole. So this is not piecewise continuous because the function is not defined at 2. But we could make it piecewise continuous by doing one small thing. We just assign a value at 2. So it could be any value except, it could be any value. Now if it is the value which we get at 2, if it is this value, then what will happen? This will be actually continuous on the interval 0 to 10. But if we assign a value like 1 or 2 or 0 or something, -1, negative, any other value, then it will be piecewise continuous. Okay, next thing is exponential order alpha. So it will be in the next video.